Let's recap what we've seen so far, because there has been quite a bit already. We saw that our neural network is just made up of a large collection of calculations that are performed using matrix algebra and a couple of activator functions, in particular ReLU and softmax. We also saw that at the end of all of our calculations, we use categorical cross-entropy to calculate our loss. Now, the loss is what we want to minimize. To understand how to do that, we need to know a bit of calculus. In particular, we need to understand derivatives. Before I define what derivatives are, I want you to keep in mind that our aim in using derivatives is to find the minimum values of a function. The function that we're going to try and find the minimum value of is the loss function, in this case, categorical cross-entropy. Let's take a look at a very simple example, a smooth curve described by the function f of x with a single minimum shown here in purple. The derivative, which we call f prime, is the slope of the tangent at any given point on f of x. The function of f prime is shown as the green line. Let's see how we got there. Given any point on f of x, we can draw a tangent line, which is like approximating a linear line over a very, very tiny distance. This line, like any straight line, can be described by an equation with y-intercept and a slope. The derivative is the slope of the tangent at any given point. In this case, it's minus 0.8. That's where the green dot is plotted. That's all it is, but why are derivatives so exciting? Well, we now know two very important pieces of information about the original function. First, it tells us what direction the original function is moving in as we increase x. If the derivative is negative, we know that an increase in x will cause a decrease in the original function f of x. In our case, the derivative of all values in the green region will be negative. We can see that in this range, as we increase x, the value of f of x will get smaller. We can summarize this by saying that we can minimize f of x by changing x in the opposite direction of f prime. If f prime is negative, increase x, and conversely, if f prime is positive, decrease x. Remember, our goal is to find the minimum point of f of x. Second, it also tells us how quickly it's moving. A large slope tells us that for a given change in x, y will change a lot compared to the same change in x where the derivative is much smaller. If we compare these two areas, we can see that f of x doesn't change much in the region on the left, but it does for the region on the right. That will be reflected in the derivatives in these regions. Note that we're not interested in direction here. Large just means far away from zero in either direction. Okay, so why is that interesting? Well, what do you think the derivative will be at the curve's minimum and maximum? How quickly is the curve changing at these exact points? It turns out that the derivative here is zero. There is no change. Think about it this way. It's like throwing a ball in the air. The velocity decreases until, for a tiny, tiny split second, the ball is actually not moving at all. We can prove this because the velocity has to change direction. It has to have passed through a velocity of zero at some point, and that occurs at the highest peak in its ascent. That's the same thing as saying that the derivative is zero at the peak of the original curve. Wherever we have an f prime of zero, we know that we're either at a maximum or minimum on f of x. Let's take a look at the whole f prime function again to see why that's interesting. The change over a small interval is really a lot where f prime is large. Now look at where f prime has values around zero. That's where the original function is leveling off, and there isn't much change. That's our signal that we're at the maximum and minimum points in f of x. So there are three important take-home messages here. First, we know we can minimize f of x by moving in the opposite direction of f prime. Second, we can find the minimum and maximum values of f of x if we can find where f prime is zero. And the third point, which is implicit in this and important for practical purposes, is that we can do these things regardless of what f prime looks like. That means we don't need to know what the original function looks like, which kind of makes sense because if we can just describe the formula for the original function f of x, we can just use that to find the minimum. We wouldn't need to worry about any of this. This is assuming that the curve is smooth, that we don't have any sharp turns in f of x. There are a lot of nice rules we can follow to get derivatives of common functions. For example, the derivative of x squared is 2x, and the derivative of the sine function is cosine. Complex functions may have a single global minimum, but they may also have many local minimums. For the time being, let's assume that we're dealing with convex functions like x squared, where we have only one global minimum and no local minimums. Okay, so now we know that the derivative is a slope of the tangent. We also have some simple rules that tell us how to find the minimum. If we know the equation of the derivative and we know we only have one minimum, then we can find that minimum analytically by simply solving for the equation f prime equals 0. If we can't do that, then we have an iterative approach. In this case, we incrementally change x in the opposite direction of the derivative until we get to the derivative of 0. So what does this have to do with tensors, and why is this so important for deep learning? I'll describe that in the next video, so let's head over and find out.